Hey guys, so what have I got for you today? I've got a really long-winded problem that doesn't really matter other than, hey, I have a geometric shape and each face has an electric field because I'm solving for the flux. So, it's 18 centimeters long, 4 centimeters tall, and 5 centimeters deep, and it's got a slant in it that's 12 centimeters long. Look, this isn't drawn to scale. Don't worry about it too much. I'm not an artist. Alright, so this entire question can be summed up by like a quote from Brad Pitt from the movie Seven. What is in the box? I don't think that's exactly how he said it. I'm also not an actor, but how much charge is in this box? So first things first, I'm going to tell you right now that these values don't matter, and there's also an identical charge on the opposite side equal to this one. But the reason these don't matter is because when you're solving for flux, each surface has a perpendicular component called in hat, which is the surface normal, which sounds like the coolest band name ever. I don't know why no one's thought of it until now, but it's my band now. So whenever an electric field is perpendicular to this surface normal, it's 0. It's negative when it's in an opposite direction, and it will be positive if it was in the same direction. It's going to be positive here, but there's a little twist to it because there's a deflection. So, first things first, we're going to solve for this given angle. Well, I mean, it's not given, but it's in the problem. So, first, find that theta. So we've got sine of theta, and if you remember from high school trig, that it's SOHCAHTOA, opposite over hypotenuse. It's 4 centimeters tall, 12 centimeters long. Plug it in and get 19.5 degrees. So the next step, find the electric flux on a surface represented by phi is equal to sigma E, which is the electric field, times in hat, or dot in hat delta A. Well, so phi is equal to 100. It's in the opposite direction of in hat, so it's negative times the lengths times cosine of 0 plus 300 plus 1, because it's sort of in the same direction, times the lengths times cosine of 19.5 degrees. Alright, so just calculating that, plug it in your calculator, 1.23 volts per meter. Alright, and then now we have to solve for the charge inside, now that we have the surface charge. So in order to do that, we're going to use a closed surface integral to solve for our charge inside. So this is an identity for Gauss's law, and we're just going to rearrange it to just solve for the charge that's inside. So we know what E naught is, that's a constant, and we just solve for this entire thing. So we're just going to plug in these values right here, and we're going to get 1.1 times 10 to the negative 11 coulombs. So that's the total charge in there. That's what's in the box.